The half-life of a highly reactive substance is 6 months. If there is 72 kilograms initially, determine the mass that remains after T months, as well as the rate of decrease of mass after 3 months. All right, so I'm just going to write out my initial equation as A is equal to A naught, oh, there's a big naught, A naught times e to the power of kt. Now, I just wrote this way just to show you that you could see in this form, you know, like instead of f of t is equal to c e to the kt. So really, we have our initial. If we want to have a function in terms of t, we really just need our k value, right? So let's solve for our k value. We can do that pretty easily because it's a half-life question, right? So half would be remaining after 6 months. So let's kind of fill that in. So let's say if our initial was 72 and then e to the power of k, and this is all happening after 6 months, so it'd be times 6. How much would be left? Well, there'd be half of the 72, so there'd be 36. You also could have just said that we start with 1 and then you ended up with a half, because watch what happens here. I'm going to divide by 72, right? And then I end up with a half. Okay, so same result. So that's equal to e to the power of 6k. Now at this point, I can take the natural log. So the natural log of a half is equal to the natural log of e to the power of 6k. So we get the natural log of a half is equal to 6k times the natural log of e, which cancels. So we get k is equal to the natural log of a half over 6. So what is our equation? We'll just going back to the beginning here. All right, so we get a is equal to, and then our initial amount was 72 times e to the power of, and then our k value here. So natural log of a half over 6, and then times t. And then you could have had t on either side, but I'll put t here. All right, so there is our equation for the mass after t months. Okay, now the second part says, as well as the rate of decrease of mass after 3 months. So the rate of decrease of mass is really talking about the derivative. So we know that f prime, actually I won't use f prime again because I changed my notation. We'll just say a prime. And we'll say at 3 months, so I'll make it a prime of t so we can have something to put in, is equal to, and it would just be a naught times e to the power of kt times k. So a prime of t is equal to, so this was just 72 times e to the power of, and then our k was the natural log of 1/2 divided by 6 times t, and then this was times k, so again just natural log of 1/2 over 6. And now we just want to find it at 3 months. So a prime of 3 is equal to, and I'm just going to kind of simplify this up as I go. I'm thinking you guys can follow along. I've got 72 over 6, right? So that would be 12. And then times, I'll put the natural log in the front. So natural log of 1/2. And then times e to the power of, and then I'm going to throw in 3 in place of t here, right? So then we're going to have to the power of natural log of 1/2. And then if there was a 3 in here for t, then this would become natural log of 1/2 over 2. So there is my exact answer, but as an approximation, we'll say that it is approximately equal to negative 5.88 And then my units here would be kilograms per month. Because this is a rate, right? This is like the slope of my line. Notice too the negative here, right? That means that we have a negative slope. That makes sense. That's a rate of decrease of the mass at that time.